Okay, so last week we looked at response of second order systems. We looked at some special cases, and then finally we looked at the most general case. Let me see, there's a table in the lecture notes. Let me see if I can find it quickly. Okay, so this is basically, so this chart here summarizes everything you need to know about the relation between the pole locations and the response of the system. And hopefully if you go through the examples and the last week's lectures, so you will easily find or learn the reasons why these relations are like that. So the real parts of the poles determine the speed of the system. If the poles are on the left hand side, then you have converging responses, but the poles closer to the midpoint give you slowly converging poles or responses. If you have poles that are far from here, the responses are fast. If you have poles on the right hand side, then you have an unstable system, and the imaginary part of the poles give you oscillations, okay, and how far you are from the real axis give you the frequency of the oscillation. So you need to know these relations here. And then last week I also told you that if you have many poles in a system, then you can divide that into second order or first order subsystems and then analyze the results by using those little systems. Or if you have a situation where you have a pole configuration as follows: you have some poles here, and then you have additional poles, but these poles are far to the left. Like, let's say you have some additional poles here. Then the responses due to these fast poles converge very fast with respect to, or compared to the responses due to these poles. Now, what we call these poles is, we call them the dominant poles, because the transient response is dominated by these poles. So let me show you a numerical example of that. So I'm going to run my little code here. So this is a second order system. We're looking at the step response of that system. I have two poles. So let me show you where these poles are. So the time constant you can find from here, about 0.6. So 1 over that is the time constant. So anyway, you see how fast the response converges. And I'm going to add a fast pole to this system. I'm going to add a real pole somewhere here. And on the right hand side, you're going to see the response of the new system, the new third order system. So I need to hit enter for that. Okay, now for the red system, there are three poles. The first two poles are exactly at the same place as the first system. I have a third pole which is way far to the left, as you see here. And if you compare the responses, it's pretty much identical, right? If you compare the overshoot and the settling time, all those characteristics are virtually the same. And that's because the pole, due to this, has a very fast converging response. In fact, the time constant is 50 milliseconds, right? So the response due to this pole converges within 0.2 seconds or something, which is somewhere here. And the rest of the response is dominated by these poles. And as a result, you see two responses that are virtually the same. And if I hit enter one more time, now we have a fifth order system, but likewise these two additional poles introduced are sufficiently fast with respect to the dominant poles of the system. Okay, again, I have the same dominant poles as the other two systems, but for this, the latest addition, the blue system, it's a fifth order system. Two more poles are located here, but the response is again pretty much the same as the other two systems, and that's because the dominant poles are the same. Okay, so hopefully this numerical example is helpful for you to understand how these poles have very little effect on the transient response. Okay. Anyway, well, okay, now let's come to this last topic of the course, which is the Routh-Hurwitz stability test. So this test is used to find the number of unstable poles in a high order system. It's explained here. Let me copy it from here. So suppose that we have an nth order system for which there is an nth order polynomial on the denominator of the transfer function, and we have the numerical values of these coefficients. Okay, so there should be n plus 1 coefficient. By using these numbers, we form an array that looks like this. So I'm going to pass this part rather quickly. So there are some simple rules, and once you know those rules, you can very easily construct this array. So first, you start by the coefficient of the highest power in your characteristic equation. A0, you put it here. Then you skip the next one, and then write the coefficient of the next term as the second element here. So the first coefficient was A0, next one is A1, you skip that one. The next one is A2, and you put that A2 number here. And you continue until the end of the polynomial. Then you come to the second row of the array. And for the second row, you start with the first coefficient you skipped, which was A1. You put A1 here. And then similarly, you put A3, A5, and continue until you finish the polynomial. So this is how you start. The first two rows, these elements come from the characteristic equation. You just copy the numbers from there. Then the rest of the array is constructed using a formula from these two rows, or the two rows previous to the row you are working on. Okay, so now we're finished writing the first two rows. We switch to the third row. For the element here, we use a formula given here. So as you can see, the elements of this third row are called B, and all these B coefficients are obtained using the numbers from the previous two rows. So this B1 is equal to A1 times A2. Bunlar çok net değil ama herhalde şeylerde okunuyordur. So A1 times A2 minus A0 times A3, which is A0 times A3, and you divide the result by A1. Okay, and it's the same formula applied everywhere. So for the B2 element, nasıl yapalım ya? Şurada birazcık renkli şey yaparsam herhalde. So for B1, you use these four numbers. For B2, your formula is here, A1 times A4. So for the red one, you use these red elements. For the next element, B2, you use these two numbers and these two numbers. You apply the same formula but using different numbers. Okay? And then once you're finished with the third row, you switch to the fourth row, and for the fourth row you do exactly the same thing you did for the previous row, but you just shift the numbers down. Nasıl yapalım? Efendim? Başka bir yolla derken? Ha, doğru olabilir ya. Ya ondan haberim yok benim. Öyle mi? Ha, tamam. Yani doğru olduğu müddetçe. Okay, so to construct the fourth row, you just shift everything down. Şöyle. Oldu değil mi? Okay, so as I said, there's just a simple formula, and once you apply this formula, you just fill up the array very easily. Okay, so once you complete this array or this table, then the first column of the table tells you if your system is stable or unstable, and if it is unstable, how many unstable poles there are in your system. Okay, so this is an important note. A necessary condition for stability is that all the coefficients of the origin characteristic equation should be non-negative. This is an important note. Nasıl yazıyorduk? Okay, so if this is your characteristic polynomial, then all these coefficients should be non-negative. So this AI coefficient should be greater than or equal to 0 for even if there is one negative coefficient, then you can immediately say that your system has at least one unstable pole without doing the array. Burada yazıyor olsa gerek değil mi? Oradan bulup kopyalayayım hemen. If there is a negative coefficient, then that means the system is unstable. You don't need to form the array. It can still be used to find the number of unstable poles. So for example, if I give you a transfer function as follows, suppose that your transfer function is 10 divided by s to the power 3 plus 5s squared plus 3s minus 1, then you don't need to do anything. You can immediately tell me that the system is unstable. Why? Because this coefficient is minus 1. That is negative. Okay. In fact, let me find the roots of that. Since I have MATLAB running here, let me quickly find the roots of that polynomial 1, 5, 3, minus 1. So we find out that the root of that and this is the unstable one, obviously, because it's on the right hand side. Evet. Well, the thing about this test is it doesn't say anything about the dynamics of the system. It only gives you stable or unstable. Otherwise, it can be unstable due to a very fast fall, or it can be unstable due to a very slow fall. We don't get to find out that information from this test. Okay, so there are these notes. These are so let me just copy over to the other file. So the first note says that if the first coefficient is negative, then you multiply the entire polynomial with minus 1 and continue, apply the test to that. Since we are interested in the roots of the polynomial, multiplying the polynomial with minus 1 doesn't change the root locations, right? For example, if I have suppose that our transfer function is like this, 1 divided by so the characteristic equation is the equation you obtain by equating the characteristic polynomial to 0. The characteristic polynomial okay, so this is a polynomial. It's a polynomial of f. If we equate the polynomial to 0, it becomes an equation, and we call that characteristic equation. Okay? And the roots of this characteristic equation are equal to Okay, so multiplying an equation with -1 doesn't change location of its roots. And then this second note here says that if you have no constant term in your characteristic equation, then that means you have roots at the origin, and you can apply the test by removing those roots. So for example, this is the example to that situation. So the lowest power of s is s squared. So there's no s or no constant term. So for that you can take s squared out of the parentheses, and you're left with a polynomial that has a constant term, and you can apply the test to the remaining constant term, remaining lower order polynomial. Okay? Doğru. Okay, so in this example, if you apply the test to this polynomial, then you will find out whether there are any unstable poles in that part. And then you will say that in addition to the poles here, there are 2 poles at the origin, because the square term there are 2 roots due to that, and they are both at s is equal to 0. And you add that to the information you obtained from applying the test to this part. Okay, so there are some examples here. We can look at these examples. Ya burada şeyi hiçbir yerde yazmamıştım sanki. Onu bir yere eklemem lazım. Onu şuraya eklemesi en kolayıydı. Onu gene geri dönüp yapayım şurada. Nasıl yapalım? Siyahla. And once you have the above array, you check the first column, the number of sign changes in the first column gives you the number of unstable poles in the system. We assume A0 is positive, greater than 0, and see below for that. Then all the numbers in the first column should be positive. Pozitif böyle olmuyor değil mi ya? Okay, so let's quickly take a look at the example. Okay, so let's see what we have. So there's a 4th order polynomial, and without computer we cannot really calculate the poles. But let's apply the test here. Şunları göstersem faydalı olur mu? So we start by 2 here, skip the next one, and the one after that is put there. We skip that one, and that last 10 is put here. And let me show the second row with red. So there's 1 here, and that goes there. The 5 here goes here. And then there's no other term, so I put 0 there. So for the third row, I applied the formula, and everything is shown here. So for this amount, turns out to be -7. The one next to it is 10. So I'm done here, and I come to the following. For that, I use these numbers here, and these numbers are found to be 45 divided by 7 and 0. And the last number here is 10. So now I conclude the stability by using the first row. Evet, oraya 0 yazabiliriz ya. So the last element in every row can be written as 0. Okay, so the number of sign changes give us the number of unstable poles. So we start with a positive number. This is positive, no sign change here. But this is a negative number. So I have 1 sign change here. And then I switch from -7 to a positive number again. So there's another sign change. So this is the second sign change. And the last one is positive again. So there are 2 sign changes here. So I can say that this fourth order polynomial must have 2 poles on the right hand side. So by using MATLAB, we can find out the exact locations of these poles. So if you do that, if you use MATLAB to calculate the poles, you find out that these are the poles of the system, and these are the 2 unstable poles. Okay? So let's take a look at another example. Again, we have a fourth order system. We construct the array as follows: 1, 2, and 3. The second row is 1 and 2. For the third array, if we use the formula, we find out that we get a 0 here, because the formula is this times this minus this times that divided by this number, and that gives us a 0. And the second element in the third row is 3. But if you try to calculate the numbers for the following row, you will see that the 0 here creates a problem, because the formula asks you to divide by this number here, and if you have a 0 in that position, then you have a divide by 0 error. So then a 0 in the first row is not allowed. So let me just write that here. We should not have a 0 in the first column, and that's because it gives divide by divide by 0 error. So in that case, there are several things we can do. In fact, there are two things that I know of. The first one is you have a 0 here, but the next element is not 0. Okay, so this is the easy case. In that case, you apply the following remedy. replace that 0 with a very small but positive number and continue the test. So if you have 0 in the first column, but the next in the same row is non-zero, then with a very small epsilon greater than 0 and continue. So let's see what we get if we do that. Okay, so this is where we had 0, right? Instead of 0, I put an epsilon and continue the test. So for the next row, I get this quantity. So before this was 0, and I would have 0 divided by 0 error. And if I replace the 0 with an epsilon, then I don't get that error anymore. But since I assume that epsilon is a very small number, this becomes a very large number. And you subtract a very large number from 2, that means this becomes a negative quantity, right? So this is always negative if you have epsilon sufficiently small. Then by putting this epsilon, I get rid of the divide by 0 error, and in the end I can complete the table, complete the array. But since I conclude that this is a negative number, I get 2 sign changes here, right? So I start with positive. This is still positive, a small but positive number. This is a negative number, and the 3 is again a positive number. So that means I again have 2 sign changes, just like the previous example. And then those 2 sign changes mean that there should be 2 unstable poles. And let's calculate those 2 unstable poles. So what are the coefficients? 1, 1, 2, 2, 3. 1, 2, 2, 3. And these are the and as you can see, there are indeed 2 unstable poles, and there are these 2 poles. So, in fact, there are 2 unstable poles, just like the test told us. Okay? Okay, so let's give a short break and continue after the break.